Thank you so much, Fabrizio. I am Kylie Stradley. I am visiting from very far away from Atlanta, Georgia, and I'm here to share with you a practical taxonomy of bugs and how to squash them. And I hope you'll excuse kind of the messiness of this presentation in my notebook. These are kind of my field notes on how to squash bugs, my field guide for debugging, and some case studies from things that I've seen. So I think that we can probably mostly agree that debugging software is like the Swiss Army knife in a developer's tool belt, like where a Swiss Army knife is like a little multi-tool that has things for to solve any kind of problem, any kind of situation you might be stuck in. And adept debuggers seem to be able to troubleshoot anything. Resolve every issue from a database that refuses connection all the way up to undefined is not a function. It seems like they always know like the next question to ask and the next path to take. And so sometimes when we watch them work, like they seem like magical, like mythical creatures, like a unicorn, right? These developers who can debug things like at all levels of the stack. And you watch them work and you work alongside them and they reassure you, or maybe if you are this unicorn on your team, you reassure your teammates that eventually you'll develop these debugging instincts. And someday like you'll become this magical unicorn too. And their deft actions make it really easy to believe that debugging only comes with intuition. Because you don't see the gears turning in their heads, you just see them working. And having worked on some consulting projects in the past, and then more recently working at a really large product company, I've often heard a phrase like this, and maybe you've heard this too working on projects. As you familiarize yourself with the application, you'll build up some debugging instincts. Or, yeah, I knew to look in this place because I have scars from the last time that happened. Or sometimes you hear something more specific that's like, when I see something like this happening, the first thing that I do is I scan the logs to see if this process is even completing, or maybe if it's sending a weird error message. So you can take that at face value, what they tell you, that eventually as you work in the application, you'll build up the instincts too. Or you can even go as far as to write down exactly what they said and memorize. When X happens, check the logs and develop your debugging instincts, as I like to call them. Or you can disabuse yourself of the notion that like these instincts are magic and that you just inherently learn them and just pick them up. Instincts are mystifying, and instincts let us make these like heroes and unicorns of each other. It's all right to praise heroic efforts, but when you turn someone on our team, another developer, into a hero, it makes that person the source of truth instead of our code. And our code should be the source of truth for how our application behaves. So maybe on your team you have something like, oh, that always breaks, oh, or I don't go to that part of the application. Or if something with that breaks, you have to ask Kate. She's the only one who knows how to fix it. So instincts and telling ourselves that they just have better instincts than us lets us pass off the hard work of communicating as a team or with our code. Lets us pass off that hard work and just lets us rely on heroes instead to kind of shoulder everything and fix all the really bad bugs. And then finally, I don't know about your team, but instincts don't scale. You can't just spin up a new instance of your resident unicorn developer like you can just spin up a new instance of AWS or a new server or a new database to replace something that's failed over or is on vacation, maybe more likely. We can't create more of these magical creatures, but I think that if we look more closely at instincts, we can do something that we all know how to do, which is use logic to apply patterns to instincts. So in object-oriented programming, we talk a lot about design patterns. I believe that there are debugging patterns. So let's look a little bit closer, a little bit more generally at the statement from before. Whenever I see X, I always check Y. I really like logic programming. I like logic languages. So I love this sentence because this is a rule set. If you use conditionals, which I'm sure we all do, case statements, switches, anything like that, then you probably see a conditional or something like that too. And in my experience, instincts or scars or like gut feelings or whatever people want to call them are just internalized rule sets. So think back to the times when someone's been telling you about how they debug something, or you're saying, hey, when that server goes down or when that thing went down, how did you debug it? And they say, oh, you know, if the API is running slow, then I assume that maybe we're getting way too many calls, we're getting way too many requests. So then I always know to go here and check to see why the requests are taking too long or why there are so many requests all at once. So it's when this, I do that. So that's the general idea of the debugging patterns. So like I said, this is my field guide. So we're kind of, yeah, that's the most fun technical difficulty I've had during a presentation. Thank you, RubyDay. Yeah. Yeah. I know better than to do that anymore. I finally learned that lesson. Right, sorry. So this is like my field guide, and so we can borrow some ideas from research scientists. And for this, I just have a couple of research methods that I'm going to apply to the case studies I'll show you and the patterns that I'll talk about. So the first thing that we have to keep in mind is that sometimes containment has to take priority over squashing. So that means that you have a bug that's on the loose and it's wreaking havoc on your production environment, and you just have to stop it. You have to kill whatever's causing that and get the app back online, get things working for users before we can actually sit down and really examine why did this happen and how can we prevent it from happening again. The next thing is we can only work with facts. So we can't make assumptions and we can't conjecture. We have to say exactly this is what is happening. And then lastly, just for this talk, I can't possibly describe how to catch every single kind of bug, but I have 4 kind of larger categories that I think most bugs fall into. So what I can do, and what is practical though, is to talk about identifying bugs by their observable attributes. So just the things that you can observe about them, their behaviors, and maybe like where you observe them. So to borrow again from research scientists, there's a branch of biology called, or a form of taxonomy that biologists use called phonetics. And they use it to identify and group living organisms by their observable attributes and their behaviors. So bugs in the natural world can be identified by their observable attributes, and bugs in the software world can be too. All right, a warning, and I think this is very fair. To facilitate this, to show you the patterns that I found, I'll have to contrive some really convenient scenarios. So we can just focus on identifying attributes and the larger, more general patterns. And also focus on the kinds of bugs that we see in live production applications. First, I said there are 4 kinds of bugs. There's 2 major types that I think kind of identified when I was doing research. I call them the upsettingly observable and the wildly chaotic. So upsettingly observable bugs are the ones that kind of make you smack yourself when you see them and you say, how could this have happened? Or shouldn't unit tests have caught this? Or even, how could this have happened again? They usually live in your code, and they're often under-tested or even untested because it's something that you're thinking, that would always go right. That would never go wrong. Don't worry about it. And then we have the wildly chaotic bugs, and these ones are much more upsetting. They seem to break everything everywhere. You can't seem to reproduce them locally on your development machine, and frankly, you're terrified to reproduce them on production. Something horrifying like, how can this port be open, but it's also rejecting connection at the same time? It seems impossible. All I know is nothing works. So those are the 2 larger types. And now that we know those 2 types are coming down towards us, let's get down to business and actually talk about how to squash them. So we have upsettingly observable bug number 1. And these are its observable attributes. Is the bug observable in production? Can it be reproduced locally? And does it seem to be restricted to one area, like maybe a specific workflow if it's a web application, or a specific data state if you notice maybe a lot of customers or users are, who have similar data are getting stuck in this state? If you answered yes to most of these questions, you might have a Bohr bug on your hands. Bohr bugs are named such because, like the Bohr model of the atom, they're simple and deterministic. And when I say that a Bohr bug is deterministic, I mean that they always provide the same output for a given input. And they're characterized by their repeatability and their reliable manifestation. So these are usually bugs that when you see them, you're like, oh, I can't believe that happened, but you know exactly how to reproduce it, both on your machine manually and in test. Bohr bugs are most commonly found in code, but they can sometimes be found hiding in server configuration, especially if you use code to configure your servers. And they like to hide out kind of in complex branching functions, classes, or config files. So anything with a lot of if-else, switch statements, conditionals. So in the wild, where do we find a Bohr bug? Validation actually can be a minefield for Bohr bugs. Validator classes are really great to unit test because of their inherent complexity. And this means it's also really easy to heavily unit test this functionality using fixtures or test fixtures without considering all the things that can affect data state. I'm sure we've all seen the cases of the 2 doors that open by not being able to open each other because they're heavily unit tested. Or things that appear to work but actually don't. And if the consequences of a failing validation fail silently, then they won't be planned for and they can't be rescued in a noticeable way. So the error never gets back to you as a developer because you don't have a test that tests fully the entire flow. You just have unit tests. And the lack of errors make you believe that your save or your submit function on your site is fine, and unit testing will lead you to believe that there's no issues with your validator. Until that is, someone needs to send an email or maybe make a purchase, and the UI tells them that they're in a good state, but the action that they wish to trigger is never triggered. So, reproduction and resolution. How can we reproduce this bug and resolve it? The Bohr bug is the friendliest of the bugs, and it's the easiest to catch. So start with this one because it'll provide a model for the rest. So replicate the Bohr bug manual on your machine. This should be easy because it's inherently easy to replicate. If this is a web application, or any application, replicate it exactly how the user would. And then write a test that mimics the replication process you just did manually. Assert that the correct thing and not the Bohr bug is taking place in the environment that the bug lives in. Write the simplest possible implementation that fixes your bug without breaking tests. And then, this is extremely important, rewrite the code to be highly readable and extendable. This way that a Bohr bug or another kind of bug can't sneak back in. When someone, like we learned this morning, who inherits your code or uses your code later is able to read it, they can understand it and they won't maybe make another mistake or let something bad sneak in. So since we're so close to the other people, I won't be quite as dramatic. But I think that our bug, we're ready to squash it. Bye. All right. Now we're on to upsettingly observable bug number 2. These are this bug's observable attributes. Maybe kind of the questions you would ask yourself. How does this work? Wait, does this work? Wait, what is this even testing? Did this ever work? If you answered yes or huh or what to any of these questions, or maybe all of these questions, you might have found a Schrödinger bug. A Schrödinger bug is a bug that, like Schrödinger's famous thought experiment, we cannot confirm the validity of without observing it directly. So you can see this bug. When we're looking at it right now, it looks like a bug, but if you don't look at it too closely, maybe you notice it kind of looks like a stick, and the appendages look like twigs. It doesn't quite look like a bug until we really look at it. And it likes to just pretend to be working code, but on closer inspection, it reveals itself to be a bug. So there's two main types of Schroding bugs now. There are those that never worked. That's pretty scary. And those that work, but not how you thought they did. And I think that's the scarier of the two. So in the wild, code that never worked. Schroding bugs that never worked often reveal themselves because of side effects. So a common hiding spot for this type of Schroding bug is around return values. When you complete a function or you save something and you end the function with a return value, you can obscure the result of the function. So a user might report that the UI shows them their template or whatever UI element has been updated because the UI shows the changes that they made. But when they look at their account later, the changes aren't there because, as we know, they're not ever saved to the database. And this could have been hiding in your code for years. Maybe you just return to the user in the view whatever they input and not necessarily what gets saved in the database. Now, the second type is similar but a little different. So it appears to work. And when you observe it, you can see that the data reaches the correct state eventually. And this manifests its code in interesting ways, but a common place to find this bug, to be able to figure out where it is in call counts. So maybe you look at a piece of code to add something new, and you realize that a particular function, honestly, sometimes the validation is being called several times over and over. So maybe the first time this validation is called, you set up the data, and then the second or the third time, or even the fourth time it gets called, that's when the data is actually saved. This means that your code's running the same path several times before executing correctly. So both of these kinds of bugs are kind of difficult because they seem to be doing the right thing. There's flags that tell you, there's external flags that look like it's completing. Maybe it's something in the UI that's displaying the wrong data or from the return value, or maybe it's something in your own code where, yes, it does eventually get there, but it takes a very winding, convoluted path, and we really don't want to do that. So when you have a bug that seems like it's doing the right thing, but it doesn't, logs are your best friend. Add logging on save and update failures to indicate why the value isn't saved. And you can also add logging at the various states of data manipulation to see what value your data is at and why. If you have changeable data, of course, that is. These things will help you verify exactly what's happening at each point in time, and they'll help you troubleshoot later. Then, this is very important too, because we're not just containing bugs, we're squashing them. If you have a Schroding bug that worked at some point in time and doesn't work now, you can use git bisect. It's just a faster way to binary search between code to find the time between now, your current bad bug state, and the last time the code worked. Doing this will hopefully help prevent you from reintroducing some bug that maybe this change was supposed to remedy before. So if at some point the Schroding bug did work, then it's good to go back in time and just make sure you don't reintroduce a new bug when you fix it. Okay, reproduction and resolution. Reproduce the broken state locally and in test. Add log statements until you can verify what causes that state. If the bug did work at some point, find the point at which it did work and make sure you don't reintroduce anything from before. And then write tests to represent the configuration and flow of the fixed state, just like we did the board bug. So I think now we're ready to squash this one too. Okay, not so bad, right? Those were pretty easy. Good news. We're moving on to the scary stuff. wildly chaotic bug number 1. Observable attributes. Does it appear non-deterministic? Does it seem to disappear once you observe or try to debug it with print statements? If you answered yes to these questions, you might be dealing with a Heisenbug. Heisenbugs are characterized by their seeming inability to be reproduced. Once you try to observe it through recreation, you may not be able to find it. Sort of, now you see it, now you don't. I did these drawings myself, and I don't have as much training in drawing as I do programming. So this is supposed to look like the moths that disguise themselves in leaves. All right, I see some nods, okay. Just want to make sure that that was communicated. Thank you for your patience with the drawings. So in the wild, or there's 2 kinds of Heisenbugs that you might come across. And the first is a Heisenbug that lives in the code. And this occurs often because debugging tools like a print statement can actually modify code. And sometimes they change the timing of execution. So this can be as a result of statements that are only evaluated when they're called. And adding a print statement forces evaluation. And it looks like the statement was called, but it was actually only called by the print. And then the second type of Heisenbug that's in the wild is one that lives in your data, or like data of very large size. So this bug seems hard to reproduce because you can't, and you shouldn't download all of a user's data onto your development machine to recreate the steps. And you probably don't realize exactly what's causing the problem because you can only see the bug on production. So you're thinking, this user's account looks fine, I'm not sure exactly what it is, but maybe it's a user with a huge volume or a user with some very specific data conditions that maybe there aren't a lot of tests around, but because it's a lot of data or it's very specific conditions, it's hard to see that from just looking at it. Since you can't replicate these bugs on your computer, you're going to have to rely on some tooling on your server and your deployment machines. So you can use profiling. Profiling measures the memory, complexity, time, and the callers of the program being profiled. So you can add profiling with many like logging tools. I like to use a tool called QCacheGrind or KCacheGrind. For some reason, it has 2 names on the website. I don't understand why. I feel like they're both equally good names, so you should use whichever you prefer. But QCacheGrind requires these callGrind formatted files. And this is one that was output by VDebug, which is a debugger I use for Vim. So you can do this on your development machine too, but you can set it up to work with any logger. So they're full of text, so it's a lot of fun to read. This is a good just bedtime read or just whenever you want to read these. But you can see that it tells you things like the file that's called, the function, the lines, how many times it's called. It's not indicated, but it tells you how long it takes the call to complete and things like that. And you can look at it like this. It's lovely. I think we can all agree this is great to read. Or you can load them into a tool like QCacheGrind and view a beautiful flame graph. And so this is quite nice because for Heisenbug in code, where we don't really know what's going on or why, and we can't reproduce it on our machine, we can take these log files and put them in here and see, and I've taped over it, but the very bottom will be the first function or the first class that's called, and then each step up is another function or class that's called, and the length of them is the duration of the call, how long it takes to execute before it completes. So that's really helpful for a Heisenbug that's in your code because you're not really sure what's being called or how it's getting in this state. And this is helpful to use profiling when maybe you don't want to log every single function. And then for a Heisenbug in data, profiling would reveal maybe how much time we're spending trying to return some huge data set. That's a common cause of a Heisenbug in data. It's just really large, or sometimes we inadvertently create a really time-expensive calculation, and a flame graph would let us know, hey, this calculation that you're running takes a very, very long time. That's why this request is running slow, or that's why this user can't load their dashboard. The calculation for their sales over time is an n+1 and it's taking forever. So flame graphs can reveal a lot of these things that we can't really see with our naked eye. All right, so reproduction and resolution. Use profiling to find out what triggers the call, what triggers the data state. Get data into this state using the application, if that's possible. If you have tools, if you have like factories where you can create a lot of data, or if you have really talented QA people on your team, they're usually able to help you create these super convoluted user situations that users get themselves into. And then get the app in that state if possible. Recreate that state and test as close as you can. And then we actually have a Bohr bug on our hands, because you know what the trigger state is and you know what the result is. So this bug is deterministic now. So we can follow those same instructions. And good news, because I am ready to squash this one. All right, our last bug. This is the scary one. Wildly chaotic bug number 2. Observable attributes. Everything is broken, literally all of it, and please send help. If you answered yes, or I really don't have time for these questions, please just tell me the answer, you might have a Mandelbug on your hands. The Mandelbug is named after its resemblance to the Mandelbrot set. The Mandelbrot set is a mathematical set that is seemingly random when it's plotted or graphed, but the set itself is just a collection of complex numbers. And it's those numbers and those numbers alone that are the single factor in creating like the highly convoluted and sometimes beautiful fractal. So it looks very complicated, and when we're looking at it in our application and all of these bad things are happening, you're thinking everything is broken. It actually might just be one thing that's broken. Doesn't that make you feel better? Yes, so it seems like everything is broken at once. And as a result of this, you're probably under a lot of pressure to get this fixed right now. And like I said, I do have good news for you. It's probably just one thing, not everything that's broken. It's likely an issue with your system and not your code. So you're probably thinking, what? I didn't sign up for this. I'm a Ruby developer. I'm a web developer, not some kind of ops wizard or a unicorn. I can't fix this. Actually, I think that you can, though. So we've talked about some patterns, and we've kind of gotten into looking at some things a little closer to the server and a little closer to the processes and less on the web side. So let's look at an on-call log. The bug is huge and everywhere at once. SQL could not connect to server. Connection refused was bubbling up all over the place. Jobs won't run, emails won't send. Every submit button on the site fatal errored. Everything's broken, but that's all right. Let's just see, let's start with the smallest thing. Can we access your servers? Okay, yes, I have an idea. So if emails aren't sending, submits are catching fire, and nothing saves, remember we set up those logs? Let's check the logs. When was the last log entry? Was it around the same time the bug started showing up? Probably, yes. You're probably thinking, well, that's not very helpful. Of course, logs aren't working. Nothing's working. Actually, it's very helpful. If logs aren't saving, that's a really good sign that it might just be one thing. If you have servers of static size that don't automatically scale, there's a good chance that maybe you've run into this. Some of you laughed. You have used up all of your disk space. And maybe you have used up all of your disk space writing everything to the logs. So let's add one more tool to your kit. Let's check the disk usage using df-h, which is one of the Linux utilities, and see if any one file or anything is using up all of our storage, and just who that might be. So the -H flag shows us the free disk usage, and the -H is supposed to show it in a human readable format for some definition of human and readable. It's actually much worse if you don't use the -H flag. This is pretty good. And if you look, you might find that actually, yes, you have written your entire disk, and so nothing can save because there's nowhere to save it. What does this mean? You made a mistake, which is fine, but it means that debugging isn't just a one-time process that we do when something really bad happens. Debugging is ongoing, so we have to be monitoring. We want to monitor our logs to make sure they're not overflowing. We want to make sure we're not seeing the same bugs come up in our logs over and over again. So as terrifying as this is, it's a valuable and an interesting lesson. So reproduction and resolution. Attempt to connect to the server and view the logs. Use df-h to find out if all the storage is being used. Can that log be killed off? Can something be rotated off? Can it be restarted at this time? If everything's broken, unfortunately, probably yes. Back up what data you still have and kill the processes and restart everything. All right, I think we're able to squash this Mandel bug. It's a really big one, so it needs a lot. So this is a practical taxonomy of bugs. From the upsettingly observable Bohr bug and Schrödinger bug to the wildly chaotic Heisenberg bug and Mandel bug. And so you actually don't need debugging instincts, and you don't need unicorns. Bye, unicorn. You have a toolkit. You have a Swiss Army knife, and you know how to observe and classify. You know how to observe and classify Bohr bugs. They're simple and deterministic. And you have the tools to turn your other bugs into simple deterministic Bohr bugs. You know how to proactively observe and classify with structured logging and verify by time traveling with git bisect. You know how to verify bugs without changing their state by using the profiling tools. You're not afraid to use Linux tools to observe the entire process, nor should you be. They're very cool. So this is my toolkit. This is my Swiss Army knife. And I'm giving it to you, and I know you'll use it well. But I encourage you to build your own toolkit and share it with your team. So I'm sure that your project, your company are probably just as much, if not even more complex than mine in unique and interesting ways. So your toolkit should probably be like an on-call playbook or something that lets people new to the team know how to debug all sorts of wild and interesting bugs that might come up in your application. None of these ideas are unique or new. These are the resources that I used for this talk, and I would encourage you to read all of them. The top two are my favorites, but they're all very good. Yep. My name, again, is Kylie Stradley. You can find me online at KaiFast. I work for MailChimp in Atlanta, Georgia. We have 5 minutes for questions. Right, so the question was about, again, is there a pattern or is there a way to find out quickly when you have these RAM hardware failures that that's the problem and it's not some other issue with server configuration or just kind of developer foolishness? I'm not 100% sure about that because that is not my area of expertise, but I would say having a well-heeled ops team would be a good way to start. Have people dedicated to that. If you have an application of size, then it's obviously very valuable that you don't have, sorry. No, not quite unicorns as much as it is. So I work for MailChimp and we have a huge ops team and I'm a web developer. I work on the API team, so I am very good at that, but I am not very good at troubleshooting hardware issues. So we're really fortunate that we have a team of people that is really good at troubleshooting hardware issues because they have had time to learn those rules and apply them and practice them. Right. I think the book is called Site Reliability Engineering, and it's written by a lot of people who did site reliability engineering at Google. And it's a collection of case studies. And this book talks about their holistic approach to site reliability. So if you have the issue where, and I'm sure a lot of us have this issue, teams are highly specialized, you know, have different people who are very good at different things, and you have this awful bug, and you know, I'm very qualified to debug things in the API or in the database, but I'm not very qualified to debug things in the hardware. They talk about their approach of getting everyone involved early. So that's an approach that we use at my company as well. We have like a war room of sorts for bugs of different degrees, and whoever's on call from the different departments works together. So we can share that knowledge, and I don't have to memorize everything all the way down to the hardware, luckily. And yeah, the name of that book, I think it's just called Site Reliability Engineering, and it's very, very good. We read it as a book club with the production, which we development, like web developer and operations teams, and it has helped us a lot. So I recommend it. Thank you so much. Other questions? If a user expects something to happen and it really shouldn't happen. Okay, I actually almost touched on this because it's very interesting, and if we run out of time, I would like to talk to you more about it. Sometimes there's a bug where a user expects something to happen and it doesn't happen how they want it to, and developers, like, we can kind of joke around and call it a pet bug or something like that because it, you know, it's kind of a joke, like they want it to be that way, but it's not that way. However, if you find that a lot of your users have some expectation and you're like, but we didn't build it that way, actually that's the time to listen to your user, and that actually is a feature and not a bug. It is harder to determine though when it's just a couple of users having that issue. If it's just maybe one or two, like a small handful, like a very small percentage of your users, maybe that's a user training issue. Maybe that's a bug in your documentation. Does that answer? Yeah. Maybe? Okay, perfect. Anything else? Yes. This happened to me. This was a client I had when I was consulting, said, log everything, we love logs so much. And I said, yes, all right, we'll do it. And the lead developer for our team was out on a week vacation. We live in the US, and so he was in Europe, so he didn't have a cell phone. And it was just me, and I was like, no, you don't understand. I'm the junior teammate. I don't know that I'm qualified to fix this. And yeah, I think I just was like, nothing will save. And I remembered like something from college where it was like, it is really easy to just write way too much to the disk. And I was like, maybe this is what happened. And I was very lucky that time. So this is the hardest one that I had to debug. It took me a long time to get there.
Thank you, Kylie.
Yeah, thank you so much.